Welcome back. We are going to look at the last part of the class that is dealing in mediums. We started with drawing and painting. We went to printmaking. We looked at photography and film. We looked at sculpture. And we're going to finish here with architecture. And then there will be a quiz and a assessment on the architecture lecture. What was your favorite thing? And then 4 other questions dealing with 4 things that you learned about architecture in the lecture. So I'm going to begin to describe what architecture is, but also kind of start as a way of transitioning from our last lecture on sculpture to architecture. So here we're looking at these small living spaces, temporary living spaces by Andrea Zettel. She's a conceptual artist, and she has designed these builders, or is the builder of these living systems. So she goes out into the desert, she builds these prototypes, these manufactured modules, and she is able to survive in the desert for a few days, being sheltered from the heat, from the cold, from the sun, and she is able to live and work. And then when she's done, able to pull up the architecture and to leave no carbon footprint, or very little carbon footprint of having been there at all. You can tell the pieces are modular. They have this kind of circular doorway cut into them, and that she can stack them, and she can also make them 2, 3, 4 wide and long if she wants to. The other interesting thing about what she's doing, when I saw the show in like 2007, it was during the feminist retrospective at MoCA, the Museum of Contemporary Art. They had another part of the museum dedicated to all the different versions that she made of these living spaces. And some of them were kind of traditional looking shacks, and others were really unusual looking, like these kind of very small toaster looking devices that I would imagine would get very claustrophobic if you spent all day and all night in them. But they also had sculptural qualities to them. So they were architecture in terms of they had a roof, they had walls, they protected you from the elements, but in the gallery they also had a quality of feeling as if they were sculptural too. So architecture demands structural stability. We move in and out of buildings, houses, schools, offices, stores, churches, bus stations, banks, movie theaters, and take it for granted that they're not going to collapse on us. So this stability is inscribed into the architect, into the construction workers who fabricate and build it, the manufacturers who fabricate the pieces, and then also the governments that ensure that these buildings aren't going to collapse. And that idea of kind of feeling as if something would collapse, I think the CCTV building built by Dutch architect Rem Koolhaas has a quality of defying that gravity a little bit, where the 2 towers lean into each other, and then there's a walkway between the towers. And then notice also that the glass that is enveloping the entire steel skeleton doesn't really tell us how big this building is. Normally you can count the windows to figure out the stories of a very tall building. We can't do that here. He has scribed into the glass these kind of arbitrary rectilinear shapes that are kind of more like diamonds than horizontal and vertical squares and rectangles, and it really confounds the space, especially because in this photograph there's nothing next to it that really lets us know exactly how big it is. The image on the right is from the Sears Tower in Chicago. This is the ledge, a box that extends off of the 103rd floor. So here you have a roof, you have a floor, you have walls, but rather than being solid and giving us a sense of stability, it's glass, and it forces your senses to deal with the feeling that you might fall, even though you're being held up by the materials. So every building is a defiance of gravity. Erecting a roof over empty space, setting walls upright, and having the whole thing stand secure. We're going to look at two different systems, the shell system and the skeleton and skin system. I think what's interesting in this picture is the cantilever that's formed here. So a cantilever is when one part of the building kind of stands without seeming to have any support, and I'm guessing that the whole thing is secured by some sort of pylons that have been driven deep into the ground, surrounded in cement, that anchor this building, that allow this part to stand without any supports underneath it, and also provide a garage for the space as well. So the two systems, the shell system is the oldest system. So most buildings that are older than the 19th century have this quality to them, like a log cabin or an adobe house. So in the shell system, you have the walls being built slowly, and as they're being built, ultimately they have to be heavy enough to support the roof. So in the shell system, you will have a building where the roof will stand, the walls will stand, but you can't have a lot of areas that are open. You can't have huge window areas. Instead, you have very small openings, and it presents a kind of darker interior space. The skeleton system, this is something that we see in modern skyscrapers with steel frames. We see this in houses and buildings where you have a skeleton built out of wood, generally studs, 2x4s, that are mass manufactured along with trusses for roofs that are then simply constructed, put together, rather than cut apart at the site itself. And because of this system, because the roof is being held by the skeleton and by the triangular trusses, what we'll find is that you can have a lot more windows, a lot more open spaces. And the stronger the skeleton is, the more that it would be something like steel girders, the wider open those windows can be. I like to show this image just to show you kind of an impossible building that could never stand because of the two factors that should be considered in any structural system, the weight and the tensile strength. So the cement, glass, and steel needed to build this building, I think, is structurally impossible. I don't think that I think there's too many cantilevers and maybe not enough support, but Photoshop can make any building seem real. So we'll be looking at tensile strength, the amount of stretching a material can withstand before it bends or breaks. When it comes to this, stone has very little tensile strength. And then steel has a lot of tensile strength. It bends, and because it bends and it sways, we're able to build 100-story buildings using steel skeletons. So the load-bearing construction would be a stacking and piling, a shell system like the Great Friday Mosque here in Genève that is built all out of mud. It is rebuilt after the rains, and then inside there's very little open space because there are a lot of posts, a lot of columns on the inside that allow for the building to be held up. So it's one of those things that could only really exist as a darkened space rather than a light-filled space like you probably are living in now if you have, say, an Arcadia door with a lot of windows to it. So the oldest forms of architecture we know of, because they're cut out of stone, have survived for thousands of years. Say a building like the Great Friday Mosque could only exist if it wasn't maintained for probably just a couple of years. And wood structures also decay, and unless you replace the wood, they also wouldn't last that long. So post and lintel, we see this in really old structures. In fact, the two posts, the stones that are upright, and then the lintel that goes over it, we have seen this at Stonehenge. And so we know that this can go back at least 5 or 6,000 years minimum. And we see this certainly in older great architecture, like in Egypt, the Temple of Amenhotep Khonsu in Luxor, built in 1390 BCE. And it is a post and lintel construction that has stood for about 4,000 years, with these massive posts that are in the style of a papyrus plant used for writing the books of the dead. And the lintels are standing. And notice that the stone, because it doesn't have a lot of tensile strength, you have to put the columns very close to each other, or these massive stones would crack and break. So there's no way that they could last. So that is also something that must be considered in this kind of structure. Okay. Sorry, there was a giant spider confronting me. That's why the silence was there. Okay. Greek buildings. So the Greek buildings, again, they are stone, and the reason that there's no roofs that you see in the ruins is that the roofs were usually made of wood or thatch. So they didn't put, if they put stone on them, you'd have to have posts every couple of feet here. But we have open spaces because of the wood roofs, but the wood roofs have decayed over a couple thousand years. So there are three basic ways that you find Greek temples, and that's what we know about Greek architecture is from the temples. So in the older of the temples, you have the Doric order, where the columns are built directly onto the floor of the temple. And then there is a capital in the form of a stylobite, a kind of bowl, and then on that would sit the area where the roof could be put up, with an architrave, a frieze, and then a cornice. And the cornice always has this protruding area that will then help to push rainwater away from the inside of the building. And you have cornices on your houses and your apartments that you live in. The second form of the ancient Greek, the classical form, is the Ionic. The Ionic now has a base which lifts the column, makes the architecture seem a little bit lighter by lifting the column. And then on the capital, you have what looks like ram's horns. And then that sits on the entablature, under the entablature. And then the latest style is the Corinthian, which the Romans also adopt. Again, with a base, fluted shafts, and then the capital is of the acanthus plant that has purple leaves, and it looks as if the cornice, frieze, and architrave and entablature are so heavy that the plant is bending, but it's holding its weight. So this is an example of the older Doric. We also find in these columns that there is an illusion to make the columns look perfectly vertical, that they get a little bit wider in the middle and they get a little bit thinner at the tops to make them appear to be perfectly vertical. Here we have the Ionic style with the ram's heads. You can tell also various bas-relief features that have been put into the capital too, and carved designs. And then we have the Corinthian. And here we see the plant of the acanthus here with the purple leaves, and that here you get a close-up of the capital, where again the entablature is pushing down on the leaves, but it is still holding. It is not breaking. So this is what the entire form of the temple would look like. So here we're looking at a small temple on the Acropolis, the giant hill where the Parthenon is at. And in the entablature The entablature is the architrave, the frieze, and the frieze generally has bas reliefs and stories on them. And then the cornices that pushes rainwater. And then we also have the triangular pediment that has another cornice on it. And the cornices, again, are pushing the water away from the floor of the building. And then once you have the pediment built, you would probably put timbers on it and then thatch and have a roof. Now, in China and in Japan, a different kind of building style, not out of stone, but out of wood formed. So the key in a building like this, in the Baoding Temple, the oldest continuous use Buddhist temple in the world for about 1,000 years, you have this heavy ceramic roof with timbers, and what's holding it up are these really thin beams here that seem impossibly small and thin to hold up such a heavy roof. So what you have to do is you have to take the force which is pushing outward from the roof. So the force is pushing outward, making these timbers want to push out. So what they created was a bracket system. And in the bracket system, it's a series of these brackets that's taking the force of the roof and pushing it down vertically. And then that vertical wood column is able to hold everything up. And a very interesting, almost miraculous kind of form of architecture that seems to be defying gravity. You also, on the trusses, you will see a distinctive curving truss, where the trusses appear not to be just flat and triangular like they are in most buildings in America, but have this kind of curving quality. And those curves are capped off typically with ceramic figurines of fish, kind of warding off evil spirits for fire. A contribution that we often associate with Rome is the arch, even though we find the arch built in Mesopotamia earlier. This is an image of the Pandugar. This is an example of the kind of engineering that came from the aqueducts from the Romans, where they are able to have water flow for hundreds of miles, where it doesn't flow so fast that it spills out of the aqueduct and not so slow that it gets bunched up and stops flowing. So here we have these double arches created here on the Pont du Gard in France. And the arch is made from having two solid posts that you then put a wooden form that you bend the wood by wetting the wood and slowly bending it. And then on top of it you have stones. So you stack the stones by cutting them perfectly, and then it's all held in place by a keystone. So there's no mortar holding any of this together. Instead, this is completely being held up by perfectly cut stones. And we see the arches developed in the Romanesque cathedrals around 1000 AD, where they have taken the arches, and we see them in barrel vaults, and we see the barrel vaults crossed on each other to make groin vaults. And from this, we are able to have somewhat open spaces and very tall cathedrals. And you can see the ribs here that are showing us the barrel vault. The next form of building after the Romanesque style and the barrel vault is the pointed arch. So with the pointed arch, they are building taller. They are also putting the weight of the building on the columns, not on the walls, exactly like you see here in the Baoding Temple. So notice there's no walls holding this up. There is simply the columns, which means that you could have glass filling in this entire space and still be enclosed. And that's exactly what happens in the Gothic era, where by pointing, the points are able to get taller. They are able then to use the walls for stained glass that bring in light of various colors, and the buildings are massive and the interior spaces are massive. Also, in the building of the Gothic cathedrals, what happened is the weight of the roof was pushing the columns out, and they hadn't at the beginning engineered everything so perfectly. So as the stones were beginning to crack in Notre Dame here, they built these flying buttresses as an afterthought. So the buttresses are further arches with piers on them that are taking the weight from the roof and pushing the weight not outward but down to the ground, and having the massive building stand now for nearly 1,000 years. From the Romans, we also get the innovation of the dome, the rounded building. So the rounded building we see in the Pantheon, built around 2,000 years ago. The Pantheon is made out of cement. It has a cement roof with a rounded dome on it. In the inside, you can tell that the inside makes a complete circle. When you walk into the building and you stand in the doorway, it is built in such a way that your eyes can see the floor and the ceiling without your eyes moving up and down. It is the limits of human vision. Now, the outside of the building is a typical kind of Greek building where we see the entablature, the pediment, we see the columns in the Corinthian style. They are massive, yes, but they don't really reveal that the inside of the building has this surprise, this open cement dome. So giant cement domes have a number of different transitions to them. In the Hagia Sophia, we see not just a circular dome that becomes a circular drum for the building. Instead, we see a circle becoming a square with these giant buttresses here and a massive interior space. And that is accomplished by using pendatives, these kind of upside down triangles here, which resolve the circle into a square. We also have domes that are lifted, and the most famous of the lifted domes we find in the Taj Mahal, where the dome is not just a simple semicircle here, but you can see it goes beyond the center point of the circle, lifted as a drum. And we also see that in the minarets, the Persian-style minarets as well, from the Mughal emperor that built this for his wife, Shah Jahan. The other interesting thing here is not only the white marble that's being used, but the reflecting pond that when you look at the Taj at the right space, it appears to be floating. And that idea of lighter architecture we have seen since the Greeks started putting the columns on bases to make them seem not as heavy on top of the floor. In the 1800s is when we start to get cast iron and ultimately steel. So cast iron is a heavier form of iron that was innovated around 1000 BC by the Hittites. Iron replaces bronze in terms of weapons. And we see here a temporary building built for World's Fair. And in this World's Fair in 1889, this was kind of showing how cast iron could create these skeleton structures that would allow you to build really big. That cast iron construction is also something that started a little bit earlier in the 1850s from Joseph Paxson, who built the Crystal Palace, from prefabricated cast iron and glass. And the look of the iron and the glass, which we see in the Eiffel Tower, is going to become the new language of modern art. Also in the 1800s, we get the balloon frame construction, that skeleton method, where they are now mass producing the wood, the 2x4s or the studs that are used in construction, and also mass producing steel nails that allow for the skeleton style building to be mass produced for housing. Steel frame construction begins with Louis Sullivan in the 1890s, where he has taken the wood skeleton and turned it into steel, a stronger, more resilient, more bendable form of iron. And from this, we are able to get the modern skyscrapers. And here in the Wainwright building, we get this tall building, and he allows us to see the verticality here on the corners. Now, we are not seeing the steel and the glass as the aesthetic of the building yet. Still surrounding it in masonry and kind of traditional carved forms that look like the decorations you might still see in the earlier Greek temples that we were looking at a couple minutes ago. However, that aesthetic that he starts, the other thing that is really important to the building of this is the invention of the elevator. Without the invention of the elevator, nobody would want to live on these top floors. And certainly building taller becomes much more difficult without the elevator as well. So by the time we get to the Lever House in 1952, we are looking at a fully modern building here, a building of steel and glass where you're showing the steel and showing the glass. And I think what's interesting on the Lever House is how they've lifted the building up on these columns. And in fact, you can walk underneath the building to get to the other block if you want to, creating an illusion of lightness here. And again, a aesthetic that is engaging us to look not at the masonry, not at the decorations, but instead the simple geometry of steel and glass itself. We have other architectural building styles being used in bridges, from suspension buildings that have large piers that are driven into the water, and then they have a curving steel cable that has vertical cables hung from it that allows then a deck to allow for a large expanse to be driven over for transportation between islands, or to have transportation that is also tall enough to allow ships to go underneath, like the Golden Gate Bridge, or the bridge that would take you into San Pedro as well. And the new kind of cable stayed structures, new one has been built in Long Beach, where you have the piers, but rather than the cable that kind of curves with the vertical cables that are under it, the suspension, we have cable stayed that now form these kind of triangular structures that hold up the deck. Reinforced concrete is also something that allows for cement buildings, which are easy to make and easy to form because cement is liquefied and you can put them into casts that then form them, but cement is brittle. So what you need is a steel rebar lattice, a steel kind of squarish kind of fence-like armature created that then you pour the cement over, that would allow for the Sydney Opera House with these giant cement decorations in the roofs that look like sails, that they can exist and be structurally stable. From reinforced steel, that's where we see houses like Frank Lloyd Wright's Fallingwater, where he builds this building out of steel as a structure, but then covers the steel in local stones. The difference between the outside and the inside is a little bit harder to see because he's the same stone on the outside of the building is the same stone as the decoration in the inside. He also was building a giant cement cantilever that goes over the waterfall and is suspended by the steel on one side. A more recent development in building in the 1960s comes from Buckminster Fuller. He has created a geodesic dome, and these geodesic domes are created out of triangles, and the triangles then form a giant dome where you see the metal and the glass. And we can find one of these in Long Beach where the Spruce Goose was housed, a giant airplane that is now used by Carnival Cruises for the cruise ships taking off. And then also digital design. So the computer has changed a lot of things, obviously, in the world. One of the things a computer does is it allows for architects to figure out the tensile strength in their materials very easily. And it allowed for Frank Gehry to twist clay and paper and then scan the twisted paper and clay and then program in the types of steel material that he would use to build his buildings. And then the computer can figure out how the building can be constructed, what the size of the building materials, the pieces will need to be, and then they can put them in giant CNC, computer numeric controlled machines. This is a smaller one here. So this would put the materials, you put the materials in the machine, and then the machine would carve it out for you. And the bigger the machine, the larger the materials are that can be carved out, like we would see in Frank Gehry's buildings. And the Disney Concert Hall in LA would be one of these. You also find various architecture using more older techniques like fabric, like tents. Here from Shigeru Ban, we are looking at a building made out of wood and fabric that at night illuminates itself. And of course, in architecture today, we are talking about sustainability quite a bit. How do we make architecture that has more efficient ways of heating and cooling itself to use less energy? And Renzo Piano created a kind of experimental building, the California Academy of the Sciences, in the turn of the millennium. He's using glass that will change its shading when the sun is out. He tried to create a garden on the roof that I think is an abject failure. It looks like they're using an awful lot of water to keep something alive that doesn't want to stay alive. Okay. So for this assignment here, you have a quiz, and then you have an assessment. What was your favorite part of the lecture? And then what 4 things did you learn? 5 questions. And that will cover that part of the class on architecture. Talk to you soon.